Okay, so an object moving along a horizontal line has v of t equals t cosine pi t over 6. Make sure that you're in radian mode. I'll show steps in both graphing and scientific, but it is easier on the graphing for sure. Okay, so go ahead and enter that into your calculator. Go to y equals, type in x cosine pi x over 6. They say the interval is from time value 0 to 11. So if you click on the window button, you can adjust your time, your x min, x max from 0 to 11. Or if you want, sometimes I like to just have around the edges a little bit. So from -1 to 12, you don't have to. And then y min, y max, typically I start off with -10 to 10. So you're only playing with 4 numbers here, x min, x max, y min, y max. It just tells you how far you want to be looking on your coordinate plane. Okay, hit graph. Okay, it's tougher on the scientific calculator because you can't see the graph. You really have to look at your table of values and just kind of use the y values to kind of help you visualize how the graph is moving. So we have an idea how the graph is going to look. Okay, so really we have to, it says create the sign line for v of t and a of t. This is the v of t graph in front of us. And we really want to know where the x-intercepts are, right? X-intercepts will be critical points for your velocity sign line. So to find your x-intercept, you're going to go to second trace and go to that 0 feature, right? That 0 button there. Okay, and then you can go to pick a point to the left of the x-intercept, hit enter. It says left bound, so you want to pick a point to the left of your target. Okay, pick a point to the right of your target, hit enter, and then you can get to that x-intercept, so 3. Okay. Yes?
How did you put the 0 and the 11?
Oh, you go to window, and then you just type in x min, x max. You can do 0 to 11, or I went a little bit to the left. I went -11 to 12.
Oh.
Yeah, so window. There you go. Okay, I want to find out this x-intercept here. So if I go to second trace, select the 0 feature. Now I'm going to pick a point to the left of this x-intercept, hit enter. And then it says right bound, so now I'm going to pick a point on the other side of the x-intercept. Doesn't matter where, as long as it's relatively close. And now you're going to make the calculator look for the x-intercept because you've given a point to the left and to the right. It'll find that point for you, 9, 0. Okay, so your velocity sign line, right, anything above the x-axis is where you're going to experience positive velocity. Anything below the x-axis is negative velocity. Okay, so we can go from 0 to 11, 3 being a critical point, 9 being a critical point. And then we know the graph doesn't exist to the left of 0. We just want to look between 0 and 3. It's above the x-axis, so positive velocity. Between 3 and 9, negative velocity. To the right of 9, positive velocity. Okay, on the scientific calculator, or the 36 Pro, you go to make sure that you are in radian mode. So go to mode, select radian. Go to table, edit function. Type in your function. Again, only use variable x cosine pi x over 6. Okay, now you're going to start at 0. And maybe at first, maybe you want to start in a larger interval, maybe 0.5 or something. And all you're doing is you're just looking to see where is the, well, first you want to kind of visualize how the graph is moving. Okay. And also you want to look to see where is my y value going to begin to change signs, right? Wherever my y value changes signs is going to be where my velocity is going to be 0. Okay, so that comes out to be a nice whole number. A lot of times it's a decimal value, but in this case you're looking for that 0, and there's another 0 that occurs right at 9. Okay, but then along the way you want to kind of look at those y values and kind of have a feel for how the graph is rising or falling. Okay. And then along the way, you can look at the y values to see, between 9 and 11, or between 3 and 9, you see negative y values. So those are negative velocities, but then to the right of 9, we're going to be experiencing positive velocity, so positive. Okay. Now, it's also asking for acceleration sign lines, so A of t. So acceleration is going to be the peaks. You're looking for acceleration being 0, so that's going to be the peaks and valleys of your velocity graph. Okay, so there's going to be some decimal value. So if I want to find a relative max on the graph, I have another feature under second trace, not 0, but you can choose max. So all maximum does is it allows you to look for a relative max if you just pick a point to the left and to the right of your relative max. So if you click on relative max, I want to look for that relative max here. So I can scroll to a point to the, it says left bound, so I want to choose a point to the left of my x-intercept. So point to the left of the x-intercept, somewhere here, right? That's to the left of my peak. I hit enter, and then I pick a point to the right of my x-intercept. Sorry, of my relative max. I hit enter, and now the calculator is going to be looking for that relative max for me. I found it, 1.64. Okay, and then I can do the same thing to find the relative min, but then I will do second trace and I will choose minimum, 1.16. Okay, second trace. You guys have it. It's in your packet. Yeah, you guys have it. It's in the back of your packet. All right, if you choose minimum, left bound, I can choose a point to the left of my relative minimum, hit enter, and then I'll pick a point to the right of my relative minimum. I hit enter to find that point for me, 6.54. Okay. And then I know that along the way, between 0 and 1.64, I'm experiencing a positive slope. So positive slope means that I have positive acceleration. And then between 1.164 and 6.54, I know I'm going to be experiencing negative acceleration because I get negative slope and then positive slope. Okay. Now on the scientific calculator, you're really having to look at the y value to see, where is my graph beginning to, is going to peak out, right? Because you know that in the beginning, your graph is rising. And you know that you see all those y values, that all those y values are rising. And it's going to rise until around 1.6. You see that 0.8, 0.86, 1.061, and then it's going to start decreasing, right? So it's somewhere between 1.5 and 2. And if I want to get a better feel for where that value is, I can just step through using smaller intervals. So you can do 0.1, for instance. And then you're looking to see where is the y value beginning to rise to hit a max So it looks like it's around here, right? It's around 1.6. Okay. Let's see. My bad. I notated it as 1.16, but it's 1.6. 1.64. All right, 1.6. You see that's where my graph, my y value hits a relative max and starts to decrease. Okay. And same thing, you just keep scrolling down until you reach around 6. And you're going to see that the graph is going to keep falling until it hits a relative minimum. And you know that relative minimum is going to happen around 6.5 because you see the y value is going to keep decreasing, but then it's going to start increasing right around here, right? Right around that 6.27, negative 6.27, and start rising, negative 6.25. So 6.5, 6.6 is going to be your, and then along the way, you map out your graph, you know that your graph is going to have this shape, right? So it's going to be rising, positive slope, negative slope, positive slope. Okay, so part B says find the time when the object is motionless. Motionless is when velocity is 0. So at time t equals 3. Because v of t is equal to 0. Okay, part C, find the velocity of the object at t equals 4 seconds. So we can just plug 4 directly in for t and just plug it in and find that value. You can plug it in manually, or if you're using 84 plus and you have your function stored under y1, you can go to vars, yvars, and type in 4 to figure out what the velocity is at that moment in time. So -2. Okay, find the acceleration. You know acceleration is the derivative of velocity. So if you go to Math 8, that d over dx feature, and you also have it on your scientific calculator, that derivative notation, right? Second ln will take you to that d over dx. So you can type in your function here, but on your graphing calculator, you can also just call that function. So I just want to know what is the acceleration of my acceleration of the object at 4 seconds. Right, -2.314 inches per second squared, right? Every time you find the derivative, your units is going to keep adding another denominator variable, denominator variable there. Part E is the object's speed increasing or decreasing at t equals 4. So increasing, decreasing speed. We compare signs between velocity and acceleration. And we see that they both have the same sign, so therefore speed is increasing. Okay, find the total displacement. Okay. Okay, so as a reminder, there's a distinct difference between displacement, distance, and position. Okay, displacement is just a definite integral. Distance is definite integral with absolute value, and then a position is adding a starting location plus displacement. Okay, so we don't want to get any of these confused. Okay, so displacement is just a definite integral. Okay, so math 9 will take you to that definite integral notation on your scientific calculator. You can also get to it using, you see that there's that second E will take you to that definite integral. And then you can put in your velocity function. Okay, displacement can be negative. Okay, so displacement here is negative 10.993. This just tells us that between 0 and 11 minutes or 11 seconds, this object is going to have a net gain of moving backwards 11 units. So if we compare the location between 0 and 11 seconds, he's going to end up 11 units backwards from where he started. Okay, each time you find the antiderivative, your units will change. Initially, you start off with inches per second, but then you take the antiderivative, you're going to lose that. You're going to lose that denominator variable. It's just going to be inches. Okay, final total distance. Final total distance is involving absolute value. So math 9, 0 to 11. You want to call that absolute value feature. Absolute value is stored under math, number, ABS. Okay, it may take a while. Okay, don't worry about H and I, you can cross those out. Okay, so J, it says find a specific location. Now we have to involve this formula here. Find any position, any destination position I'm looking for. I'm going to have a starting location plus however much progress I made over that interval. So here's my formula here. X of final position equals initial position plus displacement. So if I want to find X of 11, I want to find the location of this object, 11 seconds. I need to know where he's starting. He's starting at location 0. Or he's starting at time 0, location 3, and then we want to find the progress in that time interval. Okay, X of 0 is 3, so he's starting off at location 3. And then over that time interval, you can plug it in the calculator again, or it's already given above. So from location 3, he's going to move backwards almost 11 units. So we want to know, where does he end up? And he's going to end up at negative 7.993 on the x-axis. Okay, part K, find the average velocity. Average velocity is average value theorem. We already know this information from part F. So we know that he's going to cover a distance of 10 units or 11 units in the backwards direction. But then we're going to split that up over the course of 11 seconds. So how fast is he moving per second? He's moving at almost 1 inch per second in the opposite direction. That's his average velocity. Okay. Let's go to the back. Okay, so here we have f of x or f of t given, and we're showing that relationship between g and f. G of x equals the antiderivative of f of t. Now that tells us that there's a specific relationship here, that f is really sitting at a level below g, because integral of f is required to even make them at the same level, which tells us that f is really the derivative graph for g. Okay, so g prime is just equal to f of x. So you look at the f graph, but you're also understanding that this is your derivative graph for g. This is your g prime graph. Okay, to find g double prime, okay, g double prime is just going to be f prime, right? If I'm taking a derivative on this side, I can also take a derivative on this side. So if I want to find g of 4, I'm just going to follow whatever that rule says, right? So g of 4 just means I'm going to put x 4 where x was, and then we can take a step back and decide how that's going to help us. So integral from 2 to 4 of f of t dt. Okay, we have a graph in front of us, so we're just going to total the areas up. All these are geometric shapes here. So from 2 to 4, all this is above the x-axis. So we can do 1/2 base times height for the triangle, and then length times width for the square. So this is an area of 1/2. That's an area of 1. So 1/2 plus 1 will be 1.5. They're all above the x-axis, so no need to make any portion negative. Okay, part D, find g of -2. Again, relying on our g of x definition there. Okay, so here we're going from 2 to -2. Now, if we're trying to pull information from a graph, we prefer to read the graph from left to right. So I'm going to spend the time to actually flip the bounds, because I'm reading backwards, just more confusing to read backwards. So I'm going to flip the bounds, but as I flip the bounds, I'm also going to be pulling a negative sign outside. Okay, so from -2 to 2, I'm just going to total those areas up. And keep in mind that anything above will remain positive, but anything below is going to be negative. So this is 1, this is 1/2. And this whole thing is just going to be 1/2 base times height. So 1/2 2 times 1, that's going to be just -1. Okay, so if I total those values up from -2 to 2, I'll get 1 minus 1 plus 1/2, which is 1/2. But then there's a negative that I pulled in front, so that's going to get me -1/2. Okay, part E, find g double prime of -3.5. So g double prime means I'm going to be understanding that it is the f prime So this is the same thing as saying find f prime of negative 3.5. So negative 3.5 is around here. But I'm not looking for the point, right? That will be f of negative 3.5. I want f prime of negative 3.5. So I'm looking for the slope. So the slope of this line, I can do rise over run. That's just going to be positive slope of 1, right? Part F, on what value of x is our g graph increasing? This is the derivative graph of g, so we can't just look at this g graph or this f graph and say, okay, that's rising, that's falling. Okay, we have to understand that this is the derivative graph. So I'm going to label what I have in front of me. Anything above the x-axis is a positive slope. Anything below is negative slope. Anything on the x-axis is slope 0. Okay, so I'm going to mark all my critical points. I'm going to start at my endpoint. My critical point is negative 3, 0, and 2. All right, those are my x-intercepts. Now I'm just going to look, where is the graph above or below the x-axis? Right, above, it starts off below the x-axis. Then it goes above the x-axis, below, and above. So our G graph is increasing from negative 3 to 0, and then from 2 to 4. Okay, because G prime is greater than 0. Okay, for what values of x is G prime decreasing? Okay, so this is not G of x decreasing, the G prime decreasing. This is talking about basically we want to get information about the concavity, okay, or the second derivative. Okay, so basically we're looking at the slope. Okay, so G prime is decreasing. Now we're looking at the slope. When is the slope negative? Basically concave down will translate to G prime decreasing. So this is going to be negative slope is from negative 1 to 1. That's fine. You can say G double prime is less than 0. Okay, find the absolute extrema. So find absolute extrema. This is an extreme value theorem, remember from first semester, where if I want to find the absolute max or absolute min, I have to test the locations of the endpoints and also test the locations of my relative max, relative min. So I'm only going to depend on my G prime for that. Anytime there's a change in sign, there's a relative min, there's a relative min, there's a relative max, there's a relative min. So I'm going to test all 5 points. Okay, all 5 points are candidates for absolute max or absolute min. So I'll start off with G of negative 4. Oh, I'm sorry. It only goes from negative 1 to 3. Okay, so we only care about interval from negative 1 to 3. So we're starting at negative 1 and we're ending at 3. Okay. And everything in between. So we don't have to worry about negative 4 and negative 3. We just have to test negative 1, 0, 2, and 3. Okay, so G of negative 1. So again, go to my definition. I want to go from 2 to negative 1, which is backwards. So I'm going to flip it. Go from negative 1 to 2. And then just change the signs. Okay, so from -1 to 2, if I look at my graph here, from -1 to 2, that's going to be 1/2 minus 1, so that's going to be -1/2. But then -1/2 with the change in sign outside, that'll become a positive 1/2. Okay, g of 0. Go to my definition. My definition says replace the x as the upper bound, replace the value in the upper bound location. So I'm going to go from 2 to 0. But again, the order is not right, so I'm going to flip the bounds and change the sign. So from 0 to 2, that's just going to be -1, right? Okay. G of 2 is easy because I'm just going from 2 to 2. What happens if the bounds are the same? To 0. That means I haven't spanned any area for me to find. And then G of 3, I'm going to go from 2 to 3. No need to adjust the bounds. They're already in the correct order. So from 2 to 3, that's just going to be an area of 1/2, positive 1/2. So we have all of our candidates in front of us, and these are the only values we need to look at to find the yes. You mean G of 0? Yeah. G of 0 is, let's see, from 2 to 0, 0 to 2. Should be a positive 1, right? Yeah, sorry, positive 1. Because it was -1 to begin with, but then there's a negative that changed the sign. So that should be positive 1. Yeah, so again, from 2 to 0, from 0 to 2, the area is -1, but then because I flipped the signs or flipped the bounds, I had to change the sign to positive 1. Okay, so we have 4 candidates here. These are the only 4 values that we're looking at to see what to determine absolute max or absolute min. Between 1/2, 1, 0, and 1/2, we see our absolute max is 1, right? That's the highest y value, and the absolute minimum is 0. Okay. Number 3. Following table shows the size of an incoming wave headed towards the shore at a given moment. Use trapezoid sum with 6 subintervals indicated by the data to approximate the area of the face of the wave. So remember that we're dealing with integral here. We're dealing with area. When we're dealing with area, you're essentially multiplying the units together. Okay. So if I have feet times feet, I'm going to end up with feet squared, right? And yesterday, we may have seen other problems where you have like ounces per minute times minute. That's what ounces per minute times minute will give you ounces. So remember that this is area related, so we're always multiplying the units together. Okay, so keep that in mind. Okay, trapezoid formula is 1/2 width, height 1 plus height 2. Right, on the test, you're not going to be asked to do as many as this. Okay, this is a lot. 6 subintervals, though, we can get that practice in. So from 0 to 7, 7 to 18, 18, 24, 6. Okay. 6 subintervals. Remember, the way you find the width is you subtract the x values, right? So 7 minus 0, 7. 18 minus 7. Okay. 11. This is 6. Okay. This is 12. 8. And 9. Okay. So those are the widths. Okay. And then we got to do this each time here. So 1/2 times 7. And then the heights are just the heights that are associated with that interval, just the ends though. If your interval spans out more than 2 order pairs, you're only going to pick off the ones at the ends. Okay, so don't add up all the heights. You're only picking 2 heights per trapezoid, or 2 y values per trapezoid. So essentially, the integral from 0 to 53 of h of x dx can be approximated using area of trapezoids here. And let's skip all the plugging in, right? All this is because if you get this, then you just spend all that time multiplying or adding those values together. It'll give you 609. Okay. But the important thing here is making sure that we have the correct units. You're always, when you're dealing with antiderivative, you're always multiplying your units together. So feet times feet will give you square feet. Okay, part B is asking for you to go from 0 to 53, but using 3 middle rectangles. Sorry about those numbers or those words getting cut off there. So now we want to go back and we want to redraw our subinterval, making sure that we can span across 0 to 53 and making sure that every subinterval sees the same number of ordered pairs. They may not have the same width, but they all will see the same number of, span across the same number of ordered pairs. So I want to split this up into 3 subintervals. So I'll go from 0 to 18. Make sure that your second subinterval is going to pick up where you left off. It'll share the same order pair as the previous subinterval. So from 18 to 36, and then from 36 to 53. Those are my 3 subintervals. Subtract my x values. My x values to get the width. 18 minus 0 is 18. 36 minus 18 is 18. And then 53 minus 36 is 17. Okay. Now to find the heights, we're just going to pick off whatever we see in the middle. Okay. It may not be directly in the middle, but it is quote unquote middle relative to left and right. So rectangle 1 will be 18 times 5. Rectangle 2 will be 18 times 26. Rectangle 3 will be 17 times 7, width times height for all of them. Okay, find the average height. This is average value theorem. One over b minus a. Integral from a to b of the function. Okay, it says use the estimation from part B. So we can replace this piece with 677. Now this is square feet And we're dividing by feet, so we're back to feet, all right? So square feet divided by feet will be feet. So the average height will just be 12.774 feet. Okay, I'll come around to see if you guys have any questions. Okay, so you have that on the Y line, right? You can go to the bars, Y bars. Got to do that. It means that your velocity is decreasing by a rate of -2. It's not that it's like slow. Sorry, 53, not 15. Because I'm facing this I want relative max, relative minus.
Yeah.
Oh, wait.
Okay, 1 second. Oh my God. We don't need these more. We don't need She made it sound like she could be. All right.
What are the odds?
I think that. There's something that you're entering in, so show me how you're entering this in, because something is.
I actually did get one there. Because I always
That's the issue. We want to multiply by 30 plus 26, you have to protect 30 plus 26. Otherwise, we're gonna multiply 13, and then. Yeah, we can do that. There's also another feature, if you want to stare at that, you can also do second y, and that will get you to a nice like fraction. This is fine. When you enter at the end at 1, you can use that feature.
Oh, I knew that.
Oh, that's what you have to do. So you go.
I'm not surprised.
Amazing. 11.
Yeah, so anytime you find a derivative, let's say you start with x per minute, your acceleration is adding, dividing by time. So inches per second per second.
And then total distance is the absolute value.
The reason why it's inches is because you're multiplying by seconds. So when you have inches per second,
It's just like.
multiply by seconds, you're gonna be units. You're multiplying by seconds.
That's
Oh, yeah.
Okay, so for the windows?
And then what should the other numbers be?
Yeah, typically I like to just do negative 10 and 10. Yeah, now, if the graph looks like it's going to show you where you want to go, then you can always adjust the window, increase it, kind of, it doesn't show the whole thing, then it clicks on negative 20, and then it'll show you the lower one.
But I really only need to ever touch the head.
That's right, that's right. Only x max, 1 and 1 max.
Oh, we got
to Y1.
Yeah, scenario.
Or is it like this?
I know.
What?